One handy trick with the way degrees are set up is that after a while some amounts of degrees become easy to visualize. When you cut easy fractions of circles, your gut instinct can tell you what value of degrees they might be. Cutting a sixth of a pizza is easy, and it has the whole number 60 degrees. For that reason, let us state the obvious. The visual judgment of degrees is easy and tidy. When we look at whole number lengths along circles, we don't have an easy visual gut instinct. 4 meters looks different on 2 different size circles, and neither are easy to remember. If you wanted to measure along the circumference of a bagel and cut off 7 inches, it is a little bit awkward. So let's state that visual judgment of circumference as a length is awkward. It's all over the place. As for radians, they're just as hopeless. An easy to see fraction has an awkward number to remember, such as the simple 3/4 size cut, measuring at 4.71 radians. Easy whole number radian cuts are not so easy to remember places. So, radians are awkward in the visual judgment too. But it's okay. Us humans have all this figured out, and we have a much tidier way to visualize radians and use them for their multitasking capabilities. Spinning around the full circle, we can call it 2 pi or 6.283185307. This or that. Both of them say the same thing. Both of them are a number of radians. We just don't multiply out the pi. One is a tidy package, the other is a mess. Spinning around half a circle, we can call it pi or 3.141592654. This or that. Both are the same. One is a mess, the other is a repackaging. A quarter of a circle spin is pi over 2 or 1.5707 blah blah blah. You choose which one you want. A sixth of a circle spin is pi over 3 or 1.047 and so on. You can use either. An eighth of a circle spin is pi over 4 or 0.78539 and so on. Both are correct. A twelfth of a circle spin is pi over 6, or you could call it 0.52359877756 if you wanted to remember all that. All of these give you the exact same information. When we choose to not multiply out the pi, we get a nice, tidy representation. These are radians repackaged. Let's go through these with a closer look. The full rotation is 2 pi. That's it. A half. The circle is divided into 2, so put everything over 1, then count out 1, 2. A circle in quarters. The circle is split into 4, so put each point pi over 2, then count out 1, 2, 3, 4. A circle in sixths. The circle is split into 6, so put at each point pi over 3. Then count out 1, 2, 3, 4, 5, 6. A circle in eighths. The circle is split into 8, so put at each point pi over 4. Then count out 1, 2, 3, 4, 5, 6, 7, 8. A circle in twelfths. The circle is split into 12, so put at each point pi over 6. Then count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now stop and appreciate that the repackaged radians are tidier than the wild radians. Now when we have radians repackaged, we shall compare them to the other parts. There are radians, so they cover both the opening on the inside and the length of the curve on the outside of the slice. They communicate a consistent shape across all circles of any size. The unit is a kind of a natural unit, and the gut instinct ability to visualize them. Let's see how we can hop from one to the other. As always, start with the most obvious thing that you can say about a circle. One full rotation equals one full rotation. Obvious enough. One full rotation measured in any unit equals one full rotation measured in any unit. One full rotation measured in radians equals one full rotation measured in degrees. This is the same as writing how many radians are in one full rotation on the left, how many degrees are in one full rotation on the right. Let's focus on the right side for a moment. We know that there are 360 degrees, and we'll just put that down. There it is. Now over to the left. We will look at this in more detail than the right. We can rephrase it as how many radians are in one circumference. When you have a question that asks how many one thing are in another thing, you can write it as another thing over one thing. In this case, we have circumference over radian. Nice. But we also know the formula for a circumference is 2 pi r, where the r is radius. Let's do it. We're not done yet. A radian is the same length as the radius. Since they are both the same, let's swap one in for the other. If radius is above and below the line, let's cut it out. The one is now boring, so drop it. And there we have it. The answer to how many radians are in a circumference is 2 pi. 2 pi radians altogether. So let's wake up the other side and put them both together again. 2 pi radians is 360 degrees. Now you can have that tattooed on your bum. The words degrees and radians are set in stone. They don't move. Most of the time you leave them out. I will leave them in, but just not move them. Now we can state a few obvious things about either side here. All of these on the left will equal all of these on the right. Only some of these on the left will equal only some of these on the right. If you have half of these on the left, it means you only have half of these on the right. The amount of circle we are working with must be the same on either side. For example, how many radians are in 1/3 of a circle? How many degrees are in 1/3 of a circle? These are two questions and we will do them both at the same time. Here is our all-important statement. We are asked for a third. Fill in the left to get the radians, fill in the right to get the degrees. Work out both. You have your answers now. You can leave the radians in the repackaged method by just leaving the pi alone, or you can multiply it out to get your answer if you wish. Second example, how many radians in 30 degrees? Or convert 30 degrees to radians. These are both the same question. Here is our almighty statement. The amount of circle is given in degrees. The right part has the number of degrees and also has the unit of degrees. The left part has the number of degrees, but the unit of radians. As Isaac Newton would say, samesies, not samesies. So swing the 360 away from the side. It goes below the line. Now the right side reads as the given degrees in degrees, and the left side is the amount of radians in radians. So calculator time, and you get pi over 6 radians, or you can multiply it out. It's your choice. And you will get 0.523 radians equals 30 degrees. How many degrees in 3.8 radians? Convert 3.8 radians to degrees. Again, both questions are the same. Here is the mathematical statement for conversion again. The question gives us radians. The left side has the given radians and the unit radian. The right side has the given radians with the unit degrees. Again, samesies, not samesies. So we don't need the 2 pi. Swing it over, it goes below the line. Now with this, the right side is the amount of degrees when multiplied out. 3.8 radians is 217.72 degrees. Always remember this line. You can learn these two as well, or you can just learn the middle one and figure out the other two every time you need them. Only you can decide how you learn mathematics. You may leave out all the units and just write them in after. Some people put the unknown amount in as x, calling it the unknown variable. You're still cool in my book if that's how you want to play it. It's all the same, really.